Dr. Arjun Venkatesan is a research scientist with the New York State Center for Clean Water Technology at Stony Brook University. He is an adjunct professor in the Department of Civil Engineering. He received his PhD at Arizona State University in 2013 and his Master's of Science at the University of Nevada, Las Vegas in 2009 in the field of environmental engineering. His current research focuses on the fate, transport, and treatment of contaminants of emerging concern in natural and the built environment.
Thank you very much for the introduction. It's a pleasure to be here to share the stage with such wonderful speakers. I should let you know I'm very new to Long Island. I moved like 2 months back, so I've learned a lot from these wonderful speakers about water quality, legislations, and so many things. But the downside to follow up my presentation after all these speakers is most of my slides are already taken. Right? Most of the things that I want to talk about, it's already touched, so it's going to be a good summary presentation to conclude it, and it's going to be very short too. This doesn't work. All right. So probably you saw that figure in Supervisor Romain's presentation as well. I was afraid he was going to talk a lot about it, but I'll continue on it. So as we all know, Long Island, it's a sole source aquifer, so the entire drinking water, almost entire drinking water is coming from under the ground. Downside is if it gets contaminated, we don't have a reasonably alternative drinking water source. So it's important that we keep it clean and treat it well before we drink. So this figure that shows it shows potential contamination, how it actually enters the groundwater. So you can see that there's a lot of different sources that can contribute, like runoff from urban runoffs. Then you have landfill sources like industrial sites, like spills and leakages, and septic systems. Dr. Gobler already touched about it. But the three important things that in Long Island, which is contributing to the contamination, is the industrial source, pesticides applications on land, and septic system leakages. These three are the major sources for contamination of our drinking water. And many of you already know about it. The US EPA has a Superfund program where it has federal money to fund to clean up like hazardous waste sites. And there's a list of hazardous waste sites which we call as national priority list. And Dr. Gobler already showed this image with the national priority list. So again, it's a good reminder that there are a lot of sites here. The yellow ones are the current active sites which are being cleaned up or still contaminated. And the green ones are close to deleted sites. It's actually like, we achieved the remedial action, but it's still a lot of sites are there. And these are based on known contaminants. So these are based on regulated contaminants. On top of this, then we have this new term called contaminants of emerging concern. So what are these contaminants of emerging concern? That's the first question that's going to pop up. These are chemicals that are not regulated currently, but they occur in the environment. But there are several unknowns associated with. That's the reason we are not able to set up a regulation for these contaminants. We don't know how frequently they occur in the environment, at what levels they occur in the environment, and we don't completely understand the risks associated with these chemicals to humans and the environment. More than 40,000 organic chemicals have been identified as contaminants of emerging concern. Okay? A lot of contaminants, and we should know that each year in the United States, we generate 2,000 new chemicals. Each year we generate 2,000 new chemicals. So it's going to keep adding to this list of contaminants where we don't understand the risks. But research clearly shows one of the major sources for these contaminants in drinking waters and surface water, effluents or leaking from like cesspools and septic tanks. These are the major contaminant sources. So let's take a step back. Think about it. If wastewater is the major source, who's generating the wastewater? It is us. So many of these chemicals actually comes from us. We actually use these chemicals through various products that we use day to day as personal care products, like lotions. If anyone uses antibacterial soap, it has like contaminants that can last in the environment forever. And recently, the FDA actually banned some of these chemicals because it was concerned to the environment as well. So we also contribute a lot without our knowledge to contamination in the environment. So with respect to our center, so I also represent the Center for Clean Water Technology. Dr. Gobler already mentioned a lot about the on-site wastewater treatment system and nitrogen removal. This effort and initiative is more towards drinking water side. So our center is trying to develop novel technologies and assess how effective they are in removing and tackling these emerging contaminants that is coming as an upcoming problem. The primary objectives of this initiative is we provide grants, support to water utilities to install novel pilot treatment techniques, and we work with them collaboratively to evaluate the efficacy of these pilot treatment systems in removing the emerging contaminants. And we also perform research. We try to develop novel and technologies which can enhance the removal of these contaminants in water sources. So these are the main objectives of the center. And we already heard about this contaminant, and our center initial focus is on 1,4-dioxane. So I'm a chemist, so I'm going to give a little bit of chemistry, so please bear with me. So 1,4-dioxane, it's an industrial solvent. It's been widely used. It's as a stabilizer, purifying agent. It's also a byproduct in many of the manufacturing processes. And it's also present in like some of the personal care products. So it has a wide number of sources. The major problem with this contaminant is a likely human carcinogen, right? So current regulation, there are no federal regulation, unfortunately. There's no maximum contamination level in drinking water. However, the US EPA has developed a health advisory level of 0.35 parts per billion in drinking water. That is equivalent to like increasing the risk of cancer in 1 in a million population. The New York State, however, has an MCL which is at 50 parts per billion. Is right a little bit higher, not a little bit, an order of magnitude higher than what is the concern level. But there's a council that is formed right now, from my knowledge, and they're working towards developing a better regulation for 1,4-dioxane. So what is the issue with 1,4-dioxane? Why is it a problem right now? So it all comes to chemistry. So this chemical is a tough one. So some of its properties makes it very difficult for us to remove this contaminant from water. It is highly miscible in water. That is very soluble. It just like spreads, and you cannot really contain this contaminant. It spreads in the groundwater very quickly. It has a low vapor pressure. That is, it doesn't evaporate quickly. So like common water treatment technique like air stripping that removes volatile organic compounds, it does not work with 1,4-dioxane. It has a high boiling point, meaning it needs high energy like vaporize, and it is not like economically feasible. It has low sorption coefficient. That is, it cannot stick to solids very easily. It likes to stay in the water phase. So a typical treatment system can have like an activated carbon that actually removes contaminants by sticking to it. 1,4-dioxane doesn't work efficiently that way. And another big problem is it's resistant to biodegradation. Even microorganisms, which are known to eat many of these contaminants and remove from groundwater, they don't work effectively on dioxane, so it's resistant to it. So all these properties about dioxane makes it very difficult for us, the water utilities, to handle this chemical and treat it. However, research has shown there's one effective treatment of 1,4-dioxane, which is advanced oxidation process. There are different configurations for this treatment system, but in theory, what it does is it creates this chemical, a hydroxyl radical, which is a very, very strong oxidant. It can attack anything, any organic chemical surrounding it, and break it down into simpler forms, which is safer to handle. So this is the hydroxyl radical. So the research has shown as this is very effective in degrading 1,4-dioxane. It also enhances biodegradation. People have used a combination of advanced oxidation process to first break down the structure of the chemical, and then the microorganisms or the bacteria can do its own job and degrade it too. This is a typical setup for a UV, which is an ultraviolet radiation in combination of hydrogen peroxide, which is a chemical added to it. This is an advanced oxidation process system. You can pump out your contaminated groundwater, add this peroxide chemical to it, you mix it, and send it to a UV reactor. This is essentially like tube lights with UV radiation, which creates these hydroxyl radicals, and then it breaks down the chemical, and it's followed by a filtration system to remove it. So when we say degradation of 1,4-dioxane and using advanced oxidation process, it's not so simple. Like, you can summarize in one equation saying that it degrades and produces carbon dioxide and water. But I'm going to scare you all with a little bit of chemistry, but what exactly happens here is it goes through a number of different steps. It forms different structures, different chemicals. More chemicals are broken down to get more like chemicals. So we need to understand if it is forming anything more toxic than what it is already. So that's where we can play our part. We're trying to figure out how this chemical is breaking down, whether it's completely breaking down into safe materials, and how we're going to track it. So that's one of the research that the center is doing on this aspect. So other considerations are, of course, we need to consider the energy consumption. We can't like put in a system that takes up like a lot of energy in it. So we're looking at energy consumptions, looking at other contaminants which could be like formed unintentionally during the treatment process. We need to, of course, remove the chemicals that we add to the system so that it does not corrode the distribution system or we do not get exposed to it, and so on. So all these will be addressed. We are trying to address by doing controlled experiments in lab and also in a pilot scale treatment system in collaboration with the water utilities. So some of the ongoing efforts, so we recently issued out a request for proposals to all water utilities, and they're going to submit proposals to us, come up with their own technology or use the existing advanced oxidation process technology, and they're going to build a pilot scale treatment system to see how efficient it is in removing dioxins. And we are going to work collaboratively with them, and we're going to study the byproducts, or the unknown contaminants that might be unintentionally formed during the treatment process, and we're going to evaluate how effective these treatment systems are by working with these water utilities. And of course, we are also going to develop new methods. We're going to try to develop methods which is in tandem with EAP to enhance the removal of 1,4-dioxane, and we'll be doing our own experiments here at Stony Brook University. So that's one contaminant that I gave like a very detailed like objectives that the center is trying to attack. But the other, we are also trying to proactively focus on other emerging contaminants. And one of the contaminants that came up with some of the speakers are the perfluorinated compounds, PFAS and PFOA. So I just wanted to spend one slide on it to tell what these chemicals are, where does it actually come from. So PFAS and PFOA are actually a part of a larger group of contaminants. They're called perfluorinated compounds or perfluoroalkyl substances. This is a structure. You have a lot of fluorine, carbon, but you have like it's just chemistry here. But this chemical have been used more than 60 years, like in the industry. It's a oil repellent and water repellent. So anyone used like a Teflon nonstick, this chemical is there in that coating. So you end up probably many of you, or if not all, already have this chemical in our blood. The Center for Disease Control actually gets samples from humans, blood, serum, and so on, test for contaminants, and they show these two chemicals. They're in the top, it's being detected, and we are already exposed to some of these contaminants. But the big problem now is also present in our groundwater and drinking water sources. With all these concerns, of course, in 2000 and 2002, there was one big manufacturing company that was producing a lot of this chemical, tried to phase out these chemicals, tried to stop its production and use in products. It's 3M, by the way. And that actually showed some changes in its contamination level. In 2006, globally, they were trying to contain the generation and production of these chemicals and use of these chemicals in products. But today, there are manufacturers who use these chemicals. There are products that has these chemicals in them, and it is being released into the environment. The EPA, US EPA has recently put an advisory level of 70 parts per trillion. So if you remember the level what the 1,4-dioxane was. It was 350 parts per trillion. This is 5 times lower than that. So it has much lower level, higher treatment goal for water utility. But there are available treatment techniques which can remove 90% of these contaminants from water. But our center is going to focus on other alternative and advanced treatment systems to more effectively remove these, not just these contaminants, but look at a wide range of contaminants as well. So that, I think that's the last slide that I had. Thank you very much for the time.